We'll get to yours. Okay. All right, we got this? Everyone good? Actually, yeah, that's where I want to rotate it, around x equals pi over 2. So x equals pi over 2 is right here. I want to rotate around here. Now, to use washers, the rectangle you draw in your region must be perpendicular to your axis of rotation. My axis of rotation here is this, right? Yeah. So I need my rectangles to be perpendicular to this. Oh, so sideways, but you can't. Yeah. You can't because if you draw a rectangle in here, well, you don't have like a right and a left. This curve gets in the way. You would have to basically take these and solve these you'd have to solve that for x, right? So you'd have an inverse trig function in here, and inverse trig functions have domain restrictions. It's looking pretty bad, right, in terms of me being able to do this? Yeah. Yes?
I know it's a dumb question. Why is the reason why we can't use 2 pi and pi as the functions, is it because they're not functions, they're just lines? I think it's because they intersect.
Well, are you saying, oh, is it like the right and the left? Yeah. Okay, that would be fine until we get here. How would we get this region in here? How would we get that and that? You see? Like, yes, from here up to here, we could do right and left. Yep. But once we get past that, see, the rectangle has to flow through the entire region and always have the left and right being the same the whole time. But if you do it here and here, these two, then when you move up, it's no longer going to be valid. Make sense? Good. Good question. Any others? I thought I saw another hand. Yes?
Could you carve that up? I'm not saying that would be a good idea. But
Yeah, absolutely. Carve it up into smaller pieces. Is that what you're saying?
Yeah, like the little triangles that you're erasing right now, like in theory you could do.
You could do each. Yeah.
And then just
Yeah. Yeah. So washers, you want your rectangles to be perpendicular to your axis of rotation. Here, it's not easy to do that, right? It's a pain in the butt to do that. It would be nice if there was a method where your rectangles could be parallel to your axis of rotation, right? And we have a method for that. It's a new method I haven't introduced you to. This problem is introducing you to the idea of why we would need that method. So do you all agree that a vertical rectangle here is actually good? Because if I do a vertical rectangle in here, right, if I go vertical anywhere in there, then the top and bottom functions are always the same as I move from left to right. They're always the same two functions, right? It's the sine function on top and it's 0 on the bottom, right? So that I'm happy with. I just don't like the fact that these are parallel. So I can't do washers. What I can do instead, though, is the new method, which is called the method of shells. Okay, shells we use this when the rectangle is parallel to the axis of rotation. When your rectangle is perpendicular, you use washers. So what I always tell students is that, hold on a second. Jesus. We've gone to this year-long schedule. Do you all know about this? No. So you know how normally when you register for classes, like it's spring, right? So you're registering for summer right now if you want, but now you're going to be able to register all the way out to next summer.
Yeah, I saw that, yeah. What?
Like, yeah, so I'm having to pick my classes. I'm just getting a text from the chair of the department. Are you taking the summer of 2024 off? Not this summer. The next summer, because I haven't picked my classes yet. And I'm like, oh my God. Okay, so, okay. I'll have to go talk to her.
Is that for students too?
No, it's it's students. We have to pick our schedules first and then. Yeah, let's not get into it. Let's not get into it. It's not my idea and it's not changing, so.
Is it because I don't know policies?
I don't know why it's happening. We're just, okay. frustrating. So this, shells, we're going to use this when I was saying, the way I look at these problems is the first thing I do is I draw the region. And then once I draw the region, I determine what rectangles make sense in that region. Do I want to do vertical or horizontal rectangles in the region? Once I determine that, then I look at my axis of rotation. If my axis of rotation turns out to be perpendicular to that rectangle, then I'm going to use washers. If it turns out to be parallel, then I'm going to do shells. All right? So the region should always dictate the rectangle for you. All right? So I'm parallel, I'm going to want to use shells. Now we have not talked about how we do shells. All right? So what I'm going to do is I'm going to try and do this problem with shells without actually giving you a formal formula for it. And then, well, I gave you kind of a formula last time. Let me show you how this is going to work. We are going to take, it's going to be a little complicated. Y'all ready? I'm going to wrap this around that green dotted line. When I do that, I get something that looks like this. It's like a washer in some sense, but it's the height of the washer is actually the height of the function, right? And it gets wrapped around like that, and it looks like that, right? We call that a shell. Okay, we call it a shell. The big difference between the shell and the washer is that this distance from here to here, right? That thickness of this shell, the thickness of the shell is the width of the actual rectangle, which is dx in this case, right? That's how wide that is. Got it? If you go back and look at the washer, the thickness of the washer was your R out and R in differences. That's not what we have here. It's not R out, R in. Okay, so everyone agree that that's kind of what my shell is going to look like? Yes? Okay, I showed you all this class ago. I'm going to come through here with scissors and cut that shell open and lay it flat. So if I cut this and lay it open, it's going to look like a big like that, right? And now I'm going to try and calculate the volume of this. Okay, the volume of that little block, right? I know how thick it is. How thick is this? Dx, okay. Do I know how tall it is? Yeah, this height right here is actually the height of the rectangle, which is actually this top function minus the bottom function, right? The top minus the bottom, which for us would just be what? Sine x plus 2, take away 0, right? Because the bottom function is 0. You all following? The last thing to do is to get how long this thing is. So the length of this, and this is the trickiest part, this length, I showed you all in class last time, is you cut it, right, and you open it up, and it's actually the circumference of the circle, right? So it's the circumference, which is the distance from, we need the radius, distance from here to here, which I'm going to call this r sub x. R sub x. I'm not going to call it r, I'm going to call it r sub x. So this side should be 2 pi, right? What's the formula for circumference? 2 pi r? Yeah. I'm going to call it 2 pi r sub x. We had this discussion about, how wide this is, and I said when we do this in the limit and the integral, this basically becomes infinitesimally small, and so really the inner and outer edges are the same in the limit. So that's why I'm using a single radius. Y'all okay with that? Yeah. So what is the volume of this one little slice right here? This volume of this one shell would be 2 pi times rx times sine of x plus 2 times dx, right? That would be the volume of just this one little shell, right? And then I use the integral to add them up. Okay? What is r sub x? This is the hardest part, I think, the part that gets most students. What is rx? Well, look at it over here. It's the distance from where to where?
The axis to.
The axis of rotation to
The outside of the shell.
the outside of the shell, but the outside and inside are like the same thing.
So dx.
It's to that purple rectangle, isn't it?
Yeah. Oh.
So
Just the average.
not average. You need to find the distance from here to there. That's Rx. That's R sub x.
It's that.
Well, hold on.
That part's gonna move.
Time out. Hold on. Time out. When we do an integral and our rectangle's in here, we would integrate from where to where? Pi to 2 pi, right? That's what we're letting x vary between, right? Pi to 2 pi. So isn't our position of the rectangle always x? So this position is always x. So if I were to measure from the from the y-axis, if I measure from there all the way to the rectangle, that is x, always x, isn't it? From the y-axis to the rectangle is x. I only want the distance from this line to there.
So x minus pi over 2.
So x minus pi over 2. If this is x, then this is x. Take away that much. This part's pi over 2. Right? That's pi over 2. So this Rx in this particular problem would be x take away pi over 2. I know this looks...
R out is always x.
Your R out, no. There's no R out in this. In shells, there's no R out. In shells, there's only R sub x. Hold on a second.
What does Rx represent again?
Rx, let me say this again. Rx is the distance from the axis of rotation to your rectangle. Not the outer edge of your rectangle, not inner edge of the rectangle, just to the rectangle itself. R sub x is the distance from the axis of rotation to the rectangle, and always noting that the distance from the y-axis to the rectangle is x. Always. From the y-axis to the rectangle is x.
So what if the axis of rotation was x equals 0?
Then R sub x would be x. Right? If your axis of rotation was here, then R sub x and x are the same thing. So R sub x would be x.
That would be plus.
Yeah, so we're going to do another, we'll do one like that. Yes?
Is that because x is defined by the integral?
X is defined, the rectangle is, the position of the rectangle is defined by x.
The integral says from pi to 2 pi?
Pi to 2 pi, yes.
Because you put pi to 2 pi, you can just use regular x and then kind of put that in for x, and that's how it works, I guess.
When we do an integral with respect to x, we're letting x vary, right? From a to b. So since x is varying from a to b, the position of our rectangle is x. Like that's our left and right position. That's what x is.
And then the integral defines what it can vary.
What it starts from and ends at.
Okay, that
Yep.
makes sense.
Yeah. Okay, I want to bring something up here. Hold on.
Marley has a question.
Yeah, because on the notes you originally showed us it did have an R outline already.
Well, hold on. I'm bringing it up real quick. Six, 3, 2. Okay, what I'm going to do here, I'm going to go to our Canvas. Course notes. Here we go. Volume summary. Y'all see that in here? Okay. Let me download this. All right, this is in your notes. This is a summary of everything we've been talking about. It's colored and everything, yes. All right. Solids of revolution. Method of washers. All right, method of washers. When your rectangle is orthogonal to your axis of rotation. Orthogonal means perpendicular. What's going on here?
Orthogonal means perpendicular.
Yes. Okay, so here's what it says. If your rectangle, right, you've got two functions of x. So you have a rectangle, that makes sense to have a rectangle vertical there, right? If they're both functions of x. You have an axis of rotation. You find your r out and your r in. I use O and I just for trying to cram everything into small spaces here. All right, you find your distance. So I tell you over here what RO, Rn is. R out is the distance from the axis of rotation to the outer edge of the rectangle. Rn is the distance from the axis of rotation to the inner edge of the rectangle. And then you just use this formula. Pi integral from a to b. A and b are the limits on x. R out squared minus Rn squared dx. That is washers. Still washers. Now you have functions of y. This is what I started class with. If you need to draw your rectangle this way, and your axis of rotation is like this, then it's the same principle, right? You figure out distance from the axis of rotation to the outer edge, axis of rotation, inner edge, and then you just use the same formula. This time your limits go from C to D, that's up and down, and you go with respect to y. That's all washers. Shells is the method we use when our rectangle is parallel to the axis of rotation. So look at this. We've got two functions of x. Our rectangle needs to be vertical, right? If our axis of rotation is parallel to it, then I'm going to use a shell, and I'm going to wrap this shell around. Okay? When I do that, I get this picture. This distance from the axis of rotation to my rectangle, I call it capital R here. I just called it R sub x. Doesn't matter. It's the distance. It's this radius from here to here. X is always the distance from the y-axis to the rectangle. Always. Y-axis to rectangle. And then your formula is this. So this is, you were saying I saw R out, R in. It's this one right here. It's 2 pi. And then r is that distance from here to here. And then this right here is the height. That's this. And then the dx is the thickness. Yes?
So, like, depending on your axis of rotation is either, like, you know, like inside the y-axis or, like, farther out or something, which then if you, like, track that or
Yeah.
What if it's like x equals...
Why don't we do this? Why don't we do this? Why don't I pull a problem off of a test? Okay? And that way you see, because on a test what I do is I give you a region and then I have you wrap it around every possible thing you could think of, and that tests whether or not you understand the difference of these methods, okay? Yeah?
So if the x goes from the x-axis always, does that mean if you reverse those two?
Reverse what to?
Across the y-axis, so you put the graph on the other side and the line to the right of the axis, like that.
Mm-hmm.
Does that mean x is then from x-axis still?
Does that mean what's?
Like, because right now we have the x drawn from the
Yes.
black line to the red.
Yes.
If you put the red on the left side,
Yep.
would it still be x-axis to the red?
Would be x.
Yeah, would x still be from the
X
black
is always the distance from your axis, from your y-axis to the rectangle.
regardless of what side the red
Regardless. Yep. Yeah.
That's what I was wondering.
Yep. Let's see what I've got here. This is not the one I want. I realize y'all have questions, like there's a lot to wrap your head around here, so wrapping around, ha ha ha. Here we go. All right, there we go. You ready?
Yeah.
Man, we are dragging. We are dragging here. Okay. This says to set up the integrals but do not evaluate, which give the volume of the solid form by revolving the region bounded by these curves about these different things. So we're going to take one region and wrap it around all these different things. Okay, one problem, that's multiple problems here, right? So first we need the region, right? So y equals e to the x. Let me graph that. I want this kind of on the side, it's in my way. Let's graph it over here. E to the x, right? All right, natural log of x minus x plus 2. Graphing calculator, right? Okay. So you're allowed to have a graphing utility, right? So let me go here. Let me just graph them here. How about we do that? E to the x, natural log of x minus 2. Is that what I had? It's probably plus 2 because I don't want that down there. There we go. Okay, the other thing was x is 1 and x is 2. Kind of exaggerate that for you there. Do y'all see the region? It's between x equals 1, this region right here. Right, the top function was e to the x. The bottom function was natural log x minus x plus 2. And then that's 2 and that's 1 right there. Right? I would like us to wrap that around. I'm going to have to write this down on the side here. X-axis, y equals negative 2, y equals 10, y equals 1, y-axis, x is negative 2, x is 3, x is 1.
So this was worth like 2 questions, right?
I don't recall.
It looks like it.
Yeah, 20.
Yeah, it's 20 points.
All right. Yeah, it is what it is. So what type of rectangle looks best here, in your opinion? Vertical, right? Y'all agree? Everyone agree?
Yes.
Vertical, because you're, oh shit, it's all right. Right, our vertical rectangle looks the best. Because you've got e to the x on top, and you've got natural log x minus x plus 2 on the bottom, right? And that would be the same as I move from left to right. And my left to right's 1 to 2, isn't it? It's 1 to 2. I don't want to even think about ever making this rectangle go horizontal, right? Because then I'm going to have a mess. So I'd like to keep it vertical the whole time, which means if I ever have to rotate this way, I'm going to use shells. If I ever have to rotate this way, I'm going to use washers. So let's see. First problem over there, x-axis. If I'm going to go around the x-axis, I have my rectangle. My x-axis is actually my axis of rotation, right? So I'm just going to wrap like this. I'm going to have to move fast because I can't spend an hour on this problem. Okay, so I'm going to wrap this around the x-axis like this. Since my axis of rotation is actually my x-axis, my distance, right, my r out, my r in, are actually the functions themselves, right? E to the x, and this one is just natural log x minus x plus 2. And I'm using washers, right? Because perpendicular. So the volume, I'm ready for the answer. Okay, the answer to this one is pi. Washers always has a pi out front. Integral from where to where? 1 to 2. And then it's going to be r out squared minus r in squared. Natural log of n. I'm already doing sequences. Squared, don't forget squared, dx. Okay? Pi integral 1 to 2, outer radius squared minus inner radius squared, dx done. Okay, for the next part, if I want to do y equals negative 2, now I've got my rectangle, I've got my x-axis, and my axis of rotation's down here now, isn't it? Like that? So that changes my r out and my r in, doesn't it? My r out is actually longer now, right? It's the e to the x function plus the 2. Yeah. And then the r in, whatever, you get the idea. Yes?
Plus the L.
So that's the ln x minus x plus 2 plus 2. Do I need to label this? This is e to the x. Y'all know what those are, right?
Yeah.
So this is pi. Let's see. Let's take a volunteer, and you can only answer once. Who wants to give me this one? Go ahead.
R out minus R in. R out is EX.
E to the x
Squared
squared.
minus
Hold on. Sorry. You forgot the plus 2,
plus 2.
right? Because we have to do that plus 2.
Always the plus with something.
All that
Plus 2
squared.
minus ln x minus x plus 2 plus 4.
Plus 2. Okay, so ln x minus x plus 2 plus 2. So plus 4
Squared.
squared dx. There you go. That's the answer to the next one, right?
The integral.
I forgot the 1 and 2. Yeah. All right, good? All right, let me get rid of this. It's just in my way now, or no? I think it's just in the way now. So the next one is around where? Y equals 10. Okay, be careful here, because now we have the rectangle, right? We've got the x-axis. Our axis of rotation is actually up here, right? That's 10.
So your R out and R in.
So R out is going to be a little different. R out is this one. R in is this one.
So
Who wants this one? You got this one?
Yeah, so it's pi
Pi,
integral 1 to 2.
1 to 2.
And then you have r out, which is 10 minus
Yep.
ln of x minus x plus 2.
Okay, stop. So everyone, R out is this distance. The whole distance from here to here is 10, right? And then you got to take away this much right here, which is the natural log one. So I think I'm not going to have enough room there. So it's 10, and then you said take away the natural log x minus x plus 2,
X squared
and then all that squared minus
10 minus the other function.
10 minus, it was e to the x, right? E to the x squared dx. Is this making a little more sense that I'm doing them all together? Like, okay. All right, next one, y equals 1. This one, we haven't seen one like this. Here's my rectangle. Here's the x-axis, right? I think I need the picture for a second. Whoa, wait a minute, hold on, that's got to be.
It's like you give a graph.
Yeah, that's no, I think that might have been a typo. Yeah, because our line's in there, isn't it?
Yeah, it's like.
So let me fix that by, oh wait, yeah. Let's make it,
it's just barely touching the right.
let's make it, does a half work? Yeah, a half I think works. A half is below it. You see it right here? 1/2. On a test, I would make it very clear. This wouldn't happen. Okay. Let's change this to 1/2 instead. So basically what's happening is we have our rectangle, we have our x-axis, and our axis of rotation is here, right? Do you see?
Why did it say one word?
It was in the region.
Oh.
It was actually in the region, and we don't ever rotate within, our axis of rotation is never in the region. Shouldn't be, because it messes up the idea of volume. Okay, so let's see. Where's R out? R out is there, right? RO. And R in is there. That's real small there. Okay, who wants, not to give me the integral, who wants to tell me what R out is? Hold on. Who wants to? Yes? E to the x minus 1/2. So the distance from here to here, right, all the way down is e to the x, right? Because this is your x-axis, that's the outer edge. That distance from there to there is e to the x, but you don't want to go that far. You actually want to take off this piece right here, which is 1/2. Right, from here to here is 1/2. Y'all get that? R out being e to the x take away 1/2. So R out is e to the x take away 1/2. Who wants the next one, R in? So what's the distance from there all the way to here? That's ln x minus x plus 2, right? But you want to take away that 1/2 again to make it a little shorter, right? The distance, that distance right there is natural log of x minus x plus 2. You want to shorten it by 1/2 to give you that R in. Yeah? So natural log x minus x plus 2 take away 1/2. And then the integral. So pi integral 1 to 2. And then you've got outer squared minus inner squared dx, and then just plug those in right there, and then plug that in right there. That one was a little slower because I had messed up that line, but that all right or no? All of those we needed washers, right? Yes?
I know it's not to generalize, but if our region is above the axis of rotation, we're subtracting the function or that region from the axis of rotation, and if it's the opposite way, if it's the axis of rotation above the region.
You're asking me to generalize. You are asking, that's exactly what you're asking me to do.
Yeah.
Look, I can't give you that because look, you're saying if it's above the axis of rotation. Well, if it's here, we're subtracting it, aren't we?
Yeah.
But if it's down here, we're adding it.
Oh, okay.
You see what I'm saying?